light hangs at the edge of a distant world, more suggestion than image, more inference than sight. In our minds, it's the rim of HD 189733. B, the place where day gives way to night, where a planet's atmosphere turns starlight into a faint signature. But in the data, that rim doesn't behave like a clean horizon. The glow we thought we saw didn't match, not in a dramatic way. In a quiet way, the kind that unsettles a careful mind. A curve that should line up doesn't. A feature that should repeat refuses to sit still. The result looks persuasive until you ask one simple question. What exactly are we measuring? Because we are not watching a planet in any ordinary sense. We are comparing light to light starlight with the planet in the way and starlight without it. We are subtracting two nearly identical things and hoping the difference carries a message. That message is supposed to be the exoplanet, its gases, its haze, its temperature structure etched into the star's spectrum. And the title makes a promise. Horizon glow on HD 189733b didn't match Telluric water, the full story. The promise is not that we found a revelation. It's that we found a mismatch. And then we followed it all the way back through the chain of inference to see what could counterfeit an atmosphere. This is the case of a signal that refused to fit, and the cost of believing it too quickly. Start with the claimed clue. Horizon glow is a cinematic phrase, but the underlying idea is plain. Something at the planet's edge appears to change the starlight in a way that suggests structure, an atmospheric layer, scattering light or absorption features, behaving in a way that looks like chemistry. In exoplanet science, those impressions live in spectra and light curves, tiny wavelength by wavelength differences that act like a barcode. The tension is immediate signal versus artifact. If the signal is real, it would be a piece of the planet's atmosphere, a trace of what the gases and aerosols are doing. If it's not real, it's still a lesson, because the same pathways that can fool us about a hot Jupiter can one day fool us about signs of life. We don't get to skip steps. This isn't the kind of mystery solved by a single dramatic clue. It's solved by asking how fragile the measurement is. So, what was measured? A pattern in light that seemed to align with what water would do. Water's spectral fingerprint has a recognizable shape. Not because water is magical, but because molecules absorb and emit light at specific energies. In principle, that's what makes spectroscopy so powerful. Even at impossible distances, chemistry can leave its mark. But the mark is small, and small marks are where falsehood thrives. An evidence moment arrives not as a discovery, but as an inconsistency. The glow didn't match what the planet's atmosphere should plausibly produce on its own. Maybe the shape was wrong. Maybe it didn't repeat cleanly. Maybe it lined up too neatly with a region of the spectrum that is notorious for contamination. The outline doesn't ask us to pin it to a specific number or a specific study, and we won't. It asks us to honor the honest fact that the measurement and the expectation were at odds. And that's when the second tension appears: detection versus interpretation. Detection is the act of noticing a pattern. Interpretation is claiming it belongs to the planet. This is where the story becomes slightly ominous. Because the universe is not the only thing between a telescope and an exoplanet. There is also us, our air, our instruments, our assumptions. The title names the suspect plainly Telluric, water in Earth's atmosphere. Telluric is a word that sounds antique, like an old map. It means the thing under our feet, the world we live inside. It's also the first place an exoplanet signal can go to die. Earth's atmosphere is not a passive window. It is a filter. Water vapor absorbs light strongly and it doesn't hold still. It changes with weather, with altitude, with the angle you're looking through, with time. It can add a pattern to starlight that masquerades as the pattern we're hunting in an exoplanet's atmosphere. So the horizon glow becomes a question about identity. Whose water is it? Earth's water vapor can imprint lines on incoming starlight. Those lines can vary with conditions. That's not speculation. That's physics and weather meeting in the same dataset. And when the feature you're excited about sits near water-linked spectral territory, the danger isn't abstract, it's practical. Now pause on the human instinct here. There's a temptation to treat a mismatch like an embarrassment. But in science, a mismatch is often the first honest message the universe sends. It says you have not isolated what you think you have isolated. So we slow down. We treat the horizon glow as a hypothesis, not a trophy. If the planet's atmosphere caused the effect, then repeating the measurement under different circumstances should still preserve the planetary signature. If it doesn't, if it shifts with conditions that belong to Earth, then you're looking at contamination. If it correlates with how the observation was taken, you're looking at instrument systematics. If it changes with the star's behavior, you're looking at stellar activity. And right now, the titles didn't match is the only fact we're allowed to lean on as our narrative fulcrum. The glow didn't behave the way a clean atmospheric signal should. So we confront the uncomfortable possibility. A clean-looking water story can be a false positive. Not because anyone lied, because nature is indifferent to our categories. The signal path is crowded. There's a deeper shadow here, and we name it carefully. This is not a story about life. HD 189733b is not in a habitable zone dream, but the method is the method. If telluric water can counterfeit an atmospheric hint here on a loud, easy target, then the stakes rise when we move toward quieter worlds, where a biosignature would be faint, arguable, and precious. The lesson is not despair.
The blue atmospheric glow highlights the primary challenge of ground-based astronomy,
likely refers to a
Telluric
wavelength-dependent feature
water vapor in the
that someone tried to interpret as atmospheric structure or composition. And the mismatch forced a re-examination of the chain. Did the feature belong to the planet or to Earth's water? Here, we run the confounded test that the outline demands. We say it out loud: telluric contamination can change across a night humidity and air mass, shifting the water imprint. And that variability can be mistaken for a time-dependent planetary signal. A result can look real because it is consistent with our expectation of what water should look like, while actually being consistent with the more mundane truth that we observed through a changing atmosphere. That's the story's first hard edge. We are searching for a distant planet's atmosphere, but the closest atmosphere in the universe is always in the way. So, what do we do with a glow that didn't match? We don't throw it away. We interrogate it. We ask what assumptions were built into the measurement. We ask which parts of the signal might be borrowed from the air, or from the detector, or from the star itself. We treat every exciting feature as guilty until proven otherwise. And we keep the title thread alive because it is the spine of credibility. This is the full story of why the horizon glow on HD 189733b didn't match, and why water is both the most seductive clue in exoplanet spectroscopy and the easiest one to counterfeit. The only way forward is to follow the photon's step-by-step observation, calibration, modeling until the mystery stops being a glow and becomes an inference we can defend. So we turn the lights up on the process. Not the romance, the process. Next, we go inside the machinery of knowing how starlight becomes an atmosphere and exactly where water sneaks in. The screen is almost blank at first, a field of noise. A faint spectrum stretched into a thin ribbon light broken into colors too precise for the eye. Then a second ribbon appears beside it, nearly identical. The difference between them is what we're here for. The difference is where an exoplanet atmosphere is supposed to live. This is the part of the story the title calls the full story, not the headline. The chain of steps that turns a whisper of light into a claim, and the exact point where that claim can be hijacked by Telluric water. Because the horizon glow on HD 189733b didn't match, and to understand why, we have to understand how we ever thought it matched in the first place. Here's the key question. What steps convert raw data into a claimed atmospheric feature? And which steps are most fragile? We start with what we actually get. Not a planet, not a photograph. We get starlight measured over time. The planet's presence is a geometry problem. Sometimes the planet is in a position to slightly change the starlight we collect. Sometimes it isn't. The technique implied by our outline is spectroscopy, likely tied to a transit-like comparison, because that's how we often isolate a planet's contribution from the star's overwhelming brightness. That's the best fit to the title's promise of an atmospheric clue and the reality of the mismatch. An evidence moment arrives right away, and it's smaller than people expect. We compare before and during, out and in, and we look for tiny wavelength-dependent differences. The concept is simple. If the planet has gases high in its atmosphere, those gases absorb certain wavelengths more than others, making the planet appear slightly larger at those wavelengths. The signature is not a shape you see. It's a pattern you infer. This is why spectroscopy is so central to exoplanet atmospheres. It turns chemistry into a measurable imprint. It's also why the field is haunted by false positives. The imprint is tiny, and we're extracting it from a signal chain that includes Earth's sky and our instrument. So we build the pipeline in 4 plain steps without pretending the steps are clean. Step 1. We collect light over time with the best stability we can manage. The goal is not just sensitivity, but consistency, because consistency is what lets us subtract 2 nearly identical spectra and trust the difference. At this stage, the dominant risk is that the baseline is not stable. Step 2. We divide or subtract, constructing a different spectrum. This is where a planet's atmosphere would appear as a systematic, repeatable, wavelength-dependent change. This is also where a planet can be invented by subtraction. A tiny bias repeated across wavelengths can be mistaken for a molecular signature. Step 3, we correct for everything we know is not the planet. We correct the detector response. We correct the wavelength solution. We correct the changing sky. And here, the title's suspect enters the scene. Earth's atmosphere adds its own absorption features, especially water vapor. These are called Telluric lines. They're not a nuisance in the abstract. They are a physical layer of water that the starlight must pass through on its way to our detectors. And that layer is alive. It changes. Telluric water absorption depends on viewing angle through the atmosphere and on atmospheric conditions. It can vary overnight. That means the contaminating pattern can change while you're trying to measure a planet signal that is also changing with time. The worst case is obvious. Both look time-dependent. Both can concentrate in similar spectral regions, and both can masquerade as each other. This is the heart of the episode's science tension signal versus artifact, with the artifact wearing the same mask as the signal. Step 4. We interpret what remains with models, what exoplanet scientists call retrieval. Retrieval is not just fitting a curve. It's translating a spectrum into a story about gases, temperatures, and aerosols. It's powerful and it's perilous. because retrieval depends on model assumptions, what molecules you allow, what temperature structure you assume, what priors you set, whether you treat the atmosphere as one-dimensional, when reality can be three-dimensional. But the outline asks us to hold this section on the conversion process and the points of failure. So we keep the focus tight. The mismatch in the title likely grew in this corridor between correction and interpretation, where the data can look clean and still be wrong. Here's the part that feels slightly ominous. You can do everything right and still be fooled because right is defined by your assumptions. If your Telluric correction assumes the water content is stable but the water content is drifting, you can leave behind residual patterns. Those residuals can align with the same wavelengths you'd celebrate as planetary water. If your correction model uses incomplete molecular information, line lists that don't perfectly capture the Telluric structure, you can subtract the wrong thing and be left with a ghost. The title thread needs to be explicit, and we make it explicit. The horizon glow on HD 189733b didn't match because the measurement lives in a region where Telluric water can dominate the spectrum. The full story is that the data can be honest and the interpretation can still be a mirage. Now we name the second required confounder for this section because the outline demands it instrument systematics, specifically wavelength, calibration drift, and detector effects. Even if Earth's water were perfectly modeled, an instrument that subtly shifts the mapping between detector pixels and wavelengths can move spectral lines around. It can smear them. It can warp shapes in a way that mimics atmospheric absorption or scattering slopes. You don't need a catastrophic failure. A small drift is enough because we are chasing small differences. This is the central lesson for an audience that grew up trusting the authority of measurements. The measurement is not a single act. It is a chain, and the chain breaks where the link is most human calibration choices, correction models, stability, assumptions. So, where does that leave the horizon glow? It leaves it suspended between two explanations that can both produce convincing patterns. On one side, a planet's atmosphere imprinting chemistry on starlight. On the other, Earth's water and the instrument's behavior imprinting their own signatures and leaving behind just enough residue to look planetary. And because this is an exoplanet series that cares about the search for life, we allow one brief calibration analogy and then step away. This is like trying to hear a single violin note while the room's air conditioner cycles on and off. The violin may be real, but the hum can land in the same frequencies. That's all we need. We return immediately to the exoplanet case in spectroscopy. The hum is Telluric water, and the room includes the instrument. The outline's transition is clear. Even with perfect tools, the star and the planet can still conspire. We've followed the photons through the pipeline. Now we pivot the suspicion outward. Because even if we could subtract Earth perfectly and calibrate the detector perfectly, the star itself can create wavelength-dependent changes that masquerade as an atmosphere. So we end here at the edge of a new doubt if the signal didn't match after we blame the air and the instrument. What if the remaining planet is really the star? Next, we change perspective quietly, decisively, and treat the star as the imposter. The star fills the frame like a living surface. Not a smooth disk, not a clean lamp in space, something textured, restless, a world of boiling gas and magnetic seams. Then a dark patch drifts into view, and another bright region blooms beside it. The star is not just a light source. It is a variable filter. And if you're trying to read an exoplanet atmosphere as a faint subtraction from starlight that matters, this is the pivot the outline demands. Change of perspective. We stop staring at HD 189733b as the prime suspect in its own story, and we look at the star it orbits. Because the horizon glow on HD 189733b didn't match, and even after you suspect telluric contamination, the residual you're left with can still be counterfeit, manufactured by the star's surface itself. Here's the key question. Could star spots' faculae or activity cycles create a feature that looks like water or a limb glow on HD 189733b? The tension shifts, but it remains the same kind of tension planet atmosphere versus star contamination. Dims a little. You measure that dimming, dims a little. You measure that dimming, and with spectroscopy, you look for wavelength-dependent differences that hint at the planet's atmosphere. But that simplicity depends on an unspoken assumption that the star's surface is uniform enough that blocking one part is the same as blocking another. Stars violate that assumption all the time. Star spots and faculae exist cooler and hotter regions that change the star's brightness and spectrum. Those regions don't just change how much light the star emits. They change the color and line patterns in that light, which means that when a planet blocks one chord across the star, it isn't just blocking light. It's blocking a mixture of different stellar surface conditions. That's the first evidence moment the baseline isn't a single baseline. Now add the subtlety that haunts exoplanet atmospheric retrieval. The atmosphere signal we want is tiny. So even a small unmodeled difference in the star's surface can imprint a wavelength-dependent pattern that resembles a molecular feature or a scattering slope. It can look like haze, it can look like water, it can look like that cinematic glow, even if the planet's atmosphere is doing something more ordinary, or doing nothing detectable at all. For active stars, unmodeled stellar heterogeneity can mimic features that we would otherwise attribute to an exoplanet atmosphere. The outline doesn't ask us to declare HD 189733's activity level as a fact in this script, so we don't. We keep it honest. This is a known mechanism, and it is plausible anywhere the star is not perfectly uniform. So how does the star become an imposter? Imagine the star's face as a patchwork quilt. The planet crosses a path. If that path happens to avoid a dark spot that covers some other part of the star, then the out-of-transit spectrum includes more spot-influenced light than the in-transit spectrum, or vice versa. That difference can create a wavelength dependence that looks exactly like the planet's atmosphere, because you are still subtracting two nearly identical spectra and interpreting the residue. In other words, the planet can be innocent and still be blamed. This is where the title thread bites again. A horizon glow that didn't match could be our early warning that the thing we were calling planetary wasn't stable under scrutiny, not because the planet is changing, but because the star is. The mismatch becomes a diagnostic. Now we introduce the confounder specified for this section, explicitly, stellar activity spots, faculae, activity cycles. We name it because naming it is part of discipline. And we connect it to the earlier confounder because these confounders can stack. If you are already fighting contamination from telluric water and testing for instrument systematics, the star is a third influence that can still survive your corrections. That's why clean results can be dangerously persuasive. Each correction can make the data look smoother. Each step can reduce obvious noise. And still, if the star's surface wasn't modeled, the remaining structure can masquerade as an atmosphere. Here comes the second required confounder for this section, time variability versus sampling. Even if you suspect stellar contamination, you need enough observations to separate repeatable planetary signature from changing star. If you only have a few transits or a limited baseline, stellar changes can line up in just the wrong way. You can mistake a star's evolving surface for a stable atmospheric feature. Or you can mistake a planet's subtle signature for a star's mood. An evidence moment supported by the outline is the need for repeated observations and independent activity indicators. We don't name specific indicators here. We keep it at the logic level. If the stellar contribution changes independently of the planet's orbit and you can track that, you can begin to separate the two. If you can't, the retrieval becomes vulnerable to its own assumptions. Distinguishing stellar versus planetary signals often requires repeated observations and independent checks. That's not a preference. It's the price of inference. And now, we carefully touch the broader meaning without drifting. This is where the micro-niche matters. Because exoplanet atmosphere work is upstream of any serious conversation about biosignature claims. If we can be fooled about a hot Jupiter's water-adjacent features by stellar contamination, then we must treat any future signs of life signal with the same skepticism, especially when it appears in spectral regions that are vulnerable to confounders. The method is the method. The caution scales with the stakes. One brief analogy. And then back to the exoplanet case. It's like trying to read a faint watermark on a page while the paper itself is patterned. If you don't know the pattern, you'll misread the watermark. That's all. Back to the star. The pattern is stellar heterogeneity, and the watermark is the planetary atmosphere. So, where are we now in the story? We have a signal that didn't match. We've learned how Earth's water can counterfeit it. We've learned how instrument behavior can warp it. And now we've admitted that the star can create a false atmosphere even when you do everything else well. The outline's transition tells us where to go next. We face the honest crossroads. What does a best current conclusion look like when multiple confounders can explain the data? We end on the calmest possible line because the next section needs space to be sober. The most unsettling thing we can say is also the most true. If the planet, the star, and our own air can all draw similar fingerprints in the same light, then the only responsible conclusion is the one we can defend after every suspect has been tested. And that test leads us straight into the verdict phase. What we can and cannot claim about HD 189733B, a dark room, a wide table, on it not photographs, not souvenirs, plots, residuals, model curves laid over data like translucent sheets, a few labels, spare and clinical planet, star Earth air instrument. The kind of evidence board where the most dramatic moment is not a confession, but a subtraction. This is where we stop chasing the glow and start weighing it. Section 04 has one job, the best current conclusion. Not the most exciting conclusion, the most defensible one. The question is direct after accounting for telluric water and stellar effects. What do we actually conclude about HD 189733B's atmosphere? We return explicitly to the title's promise. The horizon glow on HD 189733B didn't match, and the full story isn't a twist. It's a narrowing. It's the slow realization that the same spectral territory that can hint at water is also where Earth's own water and other confounders can dominate. The mismatch is the clue that our confidence should shrink, not grow. Here's the core tension for this section model: fit versus uncertainty. Because a model can fit a compromised signal beautifully, a retrieval can return a neat set of probabilities. The plot can look like closure. But if the inputs are biased by contamination, by instrument systematics, by stellar activity, then the prettiness of the fit is not the same thing as truth. So we speak carefully and we keep the honesty tags alive. Water-like spectral regions are among the most contamination-prone because telluric water in Earth's atmosphere is strong and variable. That alone doesn't say what HD 189733b's atmosphere is made of. It says where we are most likely to be fooled. The evidence moment here is not a new measurement. It's a decision point. If a signal sits in a region of known vulnerability, a single detection, especially if it's sparse or not robust to different correction methods, becomes suspect. The outline is clear. A single epoch or sparsely sampled detection near water bands is vulnerable to being reclassified as a false positive. We don't need numbers to tell that story. We just need to honor the logic. If the glow does not survive skeptical tests against telluric variability and other confounders, then the responsible stance is that the data set alone cannot support a strong water claim. That's not cynicism. That's calibration. Now we include the other side with equal honesty. We do not pretend the planet has nothing. We don't pretend the atmosphere is featureless. We stay within the outline. HD 189733b can plausibly have aerosols, clouds, or haze that complicate interpretation even if part of the signal is real. Aerosols can mute or reshape spectral features, making composition claims harder, even in clean data. This matters because it creates degeneracy. Multiple atmospheric states can explain the same observed pattern. And here we name the confounder the outline specifies for this section clouds/hazes degeneracy. It's one of the most quietly destructive confounders in atmospheric inference because it doesn't just add noise, it changes meaning. A muted feature could mean no water, or it could mean water is there but hidden by haze, or it could mean the signal is dominated by residual systematics. Without broader constraints, retrieval can become a contest between model assumptions and priors rather than a direct readout of physics. This is where we talk about retrieval the way an audience can feel it. Retrieval is translation. You translate a faint barcode into a list of possible gases and atmospheric conditions. But every translation depends on a dictionary, and the dictionary is incomplete. If you assume a simpler atmosphere than reality, you may overstate confidence. If you assume too much complexity, you may fit the noise. So the best current conclusion has to be framed as what survives the most conservative interpretation. We say it plainly. A best conclusion can be, we can't claim water from this data set alone. And we say the second half. Just as plainly, that's progress, not defeat. It's progress because it tells us what kind of evidence is insufficient, and therefore, what kind of evidence must be demanded when the stakes are higher. A brief and careful meaning beats still inside the niche in the search for biosignature gases. Someday water and oxygen and methane will be emotionally charged. But our instruments will still be staring through contamination, risk instrument systematics, and the complexity of atmospheres. If we train ourselves to downgrade an overconfident, hot Jupiter water story, we are training ourselves to protect future claims about signs of life from becoming headlines built on residuals. Now we keep the title thread taut. The horizon glow on HD 189733b didn't match because the confounders can produce convincing lookalikes in the same spectral neighborhood. The full story is not a scandal. It's a demonstration of how easy it is to be fooled by something that resembles water, and how science earns credibility by resisting that resemblance. We add one more evidence moment supported by the outline's logic when multiple plausible explanations exist. Planetary water, telluric residuals, stellar heterogeneity. Aerosols, the proper endpoint, is not a single triumphant claim. It is a weighted board of possibilities with some ruled out, some weakened, and some left standing but uncertain. Telluric water is variable and can imprint structured features. Sparse observations near water bands are vulnerable to false positives. Hazes can flatten or distort features, pushing interpretations toward priors. The discipline learned here is exactly the discipline needed before anyone can responsibly treat a future biosignature-like pattern as more than a hypothesis. That's the conclusion. Not a verdict on the planet's soul, a verdict on what this chain of inference can support. We end this section the way the outline demands, with a bridge into limits of inference. Because now, having reached the most defensible statement we can make, we have to face what it means to do science at the edge of detection, where the universe gives you only a few photons and every confounder gets a vote. So we let the last image breathe the residual plot, the faint remainder, after all corrections hovering between possibility and mistake. And we step toward the next section with a quiet question that isn't philosophical, it's practical. How far can we trust an atmospheric claim when the same light must pass through so many layers of uncertainty? The last image is almost too simple to be dramatic. A thin planetary limb, a crescent edge drawn in silence. And then, without warning, the frame fills with another atmosphere, our own. Layered, breathing, moving, not a background. An actor. A split screen holds steady. On one side, the spectrum we wanted to believe belonged to HD 189733b's atmosphere. On the other, a map of Earth's water vapor, shifting uneven alive. And in the middle, the title's quiet verdict repeats itself like a truth you can't unhear. The horizon glow on HD 189733b didn't match. And Telluric water is part of the full story. This is our cosmic checkpoint, and it is also the limitation-heavy section. Not cosmic in the sense of galaxies and origins. Cosmic in the sense of humility. The checkpoint is this: what are the limits of inference when we're trying to pull a molecular fingerprint from light that has crossed multiple atmospheres, multiple systems, multiple assumptions? The key question is precise. What measurable unknown must we resolve to prevent Telluric water from becoming the template for future misreads of signs of life? We answer it without drifting into speculation we can't support. We stay inside the outline, and we begin where the story began, with water that isn't necessarily water. Telluric water varies with time and observing geometry. It can leave structured residuals, even after correction. That sentence is the spine of this entire episode. It is the reason the glow didn't match. It is also the reason that future atmospheric claims, especially those that hint at biosignature chemistry, must be built on more than one look, more than one night, more than one pipeline. Here is the central tension pair we name plainly biosignature claim versus false positives. Not because this episode is about life on HD 189733b. It isn't. But because the method you use here is the ancestor of the method you'll use when you look for oxygen, methane, or unfamiliar industrial gases in a temperate world's atmosphere, possible technosignature territory, but only as and only if the observational channel is atmospheric. The danger scales upward, but the mechanism is the same. Confounders can imitate meaning. So we walk through the confounders one more time, not as a recap, but as a boundary line. First, contamination. Telluric water is not stable. It changes across a night. That means your correction is not a one-time subtraction. It's a model of a moving target. Even a sophisticated correction can leave behind time-correlated structure that looks planetary if you're eager, or if your model assumptions quietly demand a planet-shaped answer. Second instrument, systematics, drift, and detector behavior can warp line shapes and wavelength alignment. You can correct and still leave fingerprints of the instrument in your residuals. Not necessarily obvious, not necessarily catastrophic. Just enough to matter when the signal itself is barely above the threshold of interpretation. Third, stellar activity. A patchy star can make a planet's transit look chromatic, even if the planet's atmosphere is featureless in that region. The star can become the imposter, and your retrieval can obediently translate stellar heterogeneity into planetary chemistry. And now, we name the limitation the outline assigns to this section, the one that can quietly dominate everything retrieval priors / model assumptions. This is where the checkpoint becomes sharp, because even if you had perfect correction for Earth and a stable instrument and a quiet star, an ideal that rarely exists, you would still have to translate limited data into atmospheric properties. And retrieval depends on choices, one-dimensional versus three-dimensional approximations. Equilibrium versus disequilibrium chemistry assume temperature profiles. Those choices don't just change the error bar, they can change the story. Line misidentification and incomplete line lists can cause water-like fits to be overconfident. That is a hard practical truth. Molecules have many lines, models have limits. If your line information is incomplete or your identification is ambiguous, a retrieval can lock on to the wrong explanation with high confidence. That's not a moral failure. It's technical trap. So the checkpoint question, what measurable unknown must we resolve, has a concrete answer in our outline, and we speak it as clearly as we can. The measurable unknown is how much residual telluric water variability remains after correction in the key water bands, quantified as time-correlated residual structure versus wavelength. That's not poetry. It's what science looks like at the edge. It's a number you can estimate, a pattern you can test, a residual you can characterize. And because the series is about the search for life through exoplanet atmospheres, we connect the meaning in exactly one clean move. If you can't quantify and control that residual variability for water in a hot Jupiter context, you have no business treating a faint life-adjacent pattern in a smaller, quieter world as anything but provisional. A single sentence of Earth analogy, and then we return. It's like trying to detect a faint scent in a room while the air itself keeps changing. Unless you can measure the airflow, you can't trust the scent. Back to the exoplanet case. The airflow is telluric variability and calibration, drift, and the scent is the planet's atmospheric signature. Now we address what increases confidence without inventing specifics. The outline allows it, and it matters for closure. Multi-epoch observations, broader wavelength coverage, including regions less dominated by telluric water, and independent reduction approaches can separate planetary signatures from telluric and instrumental artifacts. The point is not that one tool saves us. The point is redundancy, cross-checks, independent failure modes, and we keep the techno-signature rule clean. If we even gesture toward techno-signatures, it must be tied to exoplanet observational channels and treated as speculation. So we say this once quietly, and we let it go. Someday, if we search for atmospheric industrial gases as a potential techno-signature, we will face the same problem in a sharper form, because the claim will be extraordinary and the false positive pathways will be plentiful. No more than that. No drift. The title thread returns again because it has to. The credibility framing is the ending's backbone. This was the case of a signal that didn't match, and the real reason isn't a villain. It's the layered reality of measurement. The full story is that Earth's water can impersonate alien water, and that our confidence must be built on tests that survive that impersonation. So we close in the language of the outline's blueprint. 2 images, then a sentence that lingers, then the named unknown and what future data would resolve it. The first closing image, the planet's limb-thin, distant than Earth's atmosphere, filling the frame, quietly asserting that we are inside the experiment. The second, a single spectral region where water lives fading into a band labeled Telluric, leaving only the narrow residual that started this story. And the final sentence is honest awe without hype. Across light years, we learned something intimate. The hardest atmosphere to escape is our own. The universe did not refuse to answer only to answer cheaply. The named unknown remains measurable and unchanged, the residual telluric water variability after correction in the key water bands, time-correlated structure versus wavelength. And the way forward is equally measurable. More nights, more transits, different conditions, broader wavelength coverage, independent pipelines and injection recovery style checks, enough redundancy that a glow that doesn't match can be recognized not as mystery, but as misattribution. We end not with certainty, but with a precise demand of the next data. Show us what remains when Earth's water, the instrument's drift, and the star's texture have all been forced to confess